This is just a brief talk to call your attention to an analogy that exists between, on the one side, block designs, and on the other side certain electrical networks. Let me show by an example how you can construct an electrical network from a block design. Let us take as a first example the smallest balanced incomplete block design you can think of, namely the one with 3 treatments arranged in 3 blocks. So block 1 is treatments 1 and 2, block 2, 2 and 3, and then 1 and 3 in the last block. Now, from this design, we construct a network in the following way. We represent each block by a point, and each segment is also represented by a point. I'll draw them in a slightly different way to distinguish. The blocks could be drawn like this. Maybe we should call them something. Roman 1, 2, and 3. 1, 2, 3. And the treatments are represented by a point which are drawn like this. And then I'll let this be treatment number 1, and this number 2, and this number 3. And then the idea is that whenever a treatment is in a block, you draw the corresponding connection. So for example, in block 1 we have treatments 1 and 2. In block 2 we have treatments, oh that was bad, I'll interchange these like that. In block 2 we have treatments 2 and 3. And in block 3 we have 1 and 3, like that. Now, this graph is well known in design of experiments, but the interpretation of it as an electrical network seems to be a relatively rare idea. The idea is to think of each of these connections as a resistance, a unit resistance, which means that I really ought to draw them like this. 1 ohm, like that. And it turns out now that the properties of this network are closely connected to well-known concepts related to the design. The first observation you can make is that resistances through the network coincide with contrast variances in the design. To be more specific, in the design, in the usual additive model, block plus treatment structure, if you think of it that way, you can talk about the intra-block analysis. You can estimate differences between treatment parameters, and these contrasts will have some variances, which are the form of constant times sigma square. And these constants turn out to be resistances through the network here. For example, if we think of the resistance from this point to this point, so you should imagine a situation where we put on the potential difference between these 2 points and leave all other points untouched. Then the resistance through the network here will, except for the factor sigma square, be equal to the contrast variance, the variance you get when you estimate the difference between the parameter levels 1 and 2. The most important thing about this analogy is perhaps that it gives an intuitive interpretation of contrast variances, which I personally think is much easier to handle easier to understand than the concept in the statistical context. Because obviously the idea of a good design is then a design for which these resistances are small, which in some sense means that it should be a compact configuration of some kind. It should be as connected as possible. By the way, the concept of connectedness of a design is represented here as connectedness, of course. Connectedness means exactly that, for design means exactly that the network here is connected in the obvious sense. You can make various applications of this. One immediate application is that you can use it for direct computation of these contrast variances in some situations. For example, in this one, if you recall what you learned in school in physics about combination of parallel and serial combination of resistances, then you can immediately see here that the resistance through the network from this point to this point can be thought of as a parallel combination of a resistance of 2 this way and of 4 this way, which means that you will get the expression 1 over 2 plus 1 over 4 to the minus first, which is 4 over 3. Meaning in the statistical context that the variance on the difference between parameters alpha 1 and alpha 2, if that is what we call the freedom parameters, would be 4 over 3 times sigma squared. An immediate generalization of this design is a design which has a similar cyclic network. I'm thinking of a design of the form treatment, a design with block sizes 2 and with the number of blocks equal to the number of treatments, each treatment being repeated twice. So 1, 2, 3, 4, and so on, ending up with perhaps you could call it n, then we end up with n minus 1 n, and then just to close the circle, n1 here. A design like this would have a graph looking like this, except that it would be bigger, consist of a whole circle looking like this, and so on. And of course you can immediately compute the contrast variances in this network by a rule similar to that one. So that makes it easy for this special case to compute the contrast variances, and also to, if you wish, to compute their average and thereby get the efficiency. You can also, it is also rather obvious if you look at this picture that in exactly this situation you can do better. Shah said something about it the other day. We were talking, I don't remember which session it was, but at some session we talked about designs of with block size 2. It is relatively obvious here that you can do much better. For example, a design where you select, a design having a graph like this, where you select a baseline treatment, so to speak, for example number 1, and then put that in block together with all the others. So you get a graph looking like this instead. The corresponding table would then be 1, 2, 1, 3, and so on, ending with 1 n. And then an additional block. If we want to keep the number of blocks constant, we should have an additional block here, but that is not so important. The important thing to notice is that it is immediately obvious that this design is better than this design, because you can tell if you have a little feeling for how electricity behaves, you can see it immediately. Other applications, I would like to say here, even if it is not essential, the way I have constructed, I gave a talk the other day, some of you may have heard it, about an algorithm for generation of nearly optimal designs. And in that context, I found it quite useful to think of designs in terms of networks. The operations that are supposed to improve the design, which I prefer to call switches, have an interpretation in the network context which is easy to understand. The idea was simply that whenever you can take a block and a treatment, and another block and another treatment, and then you can delete these connections and introduce these connections instead. That is the operation of which I call a switch, and which Eggleston and Jones called an interchange procedure, corresponding to the idea that you just take 2 treatments and interchange them in the table. Another application you can make has to do with the idea of short-circuiting electrical networks. It is obvious that, well, I should perhaps mention first that there are other examples than these where you can use the network to compute contrast variances explicitly. For example, you can do it in balanced designs. The balanced incomplete block designs, it is quite easy to see that to see from the network what the contrast variances will be. The reason for that is that there are certain symmetries which mean that the potential at some points will be the same, and therefore you may short-circuit these points into a single point. In a balanced incomplete block design, if we think of two treatments, then, as we know, they will meet in a fixed number of blocks. So we will have lambda connections to some common blocks, the blocks in which they both occur. Maybe I can draw it like this. And then they are indirectly connected. There are lambda connections here. Then there are also some connections to blocks. This treatment has also connections or is in blocks where the other treatment is not found. So there will be some connections to that kind of blocks here, and similarly over here be some connections. And then we have all the other treatment points which may occur in this block and may occur here and may occur here. I'm not going to go into details with this. All I'll say is that it is possible to argue that in a balanced incomplete block design you can draw it like this. You can, for example, take the blocks in which both treatments occur and short-circuit in the sense that you contract all these points to a single point. And similarly, you can do it for the other treatments, you can do it for these blocks and these blocks. And then you get a picture like this, where it is easy to compute the contrast variance directly or the resistance directly, just by making use of the usual laws for serial and parallel combination. The idea of short-circuiting is applied here to do short-circuiting in a context where it is allowed, because the potentials at the point which I short-circuit here are the same, and therefore this short-circuiting will not have any influence on the resistance through the network. But what happens in general if you take groups of points and short-circuiting into a single point is that the resistance through the network will become smaller, of course. And that gives you some inequalities. That will give you some upper or lower, let's see, lower bounds for the contrast variances, and thereby you can use them also to make some upper bound by averaging for the efficiencies. These upper bounds are unfortunately not as good as those found in the literature, but anyway they are easy to interpret and quite interesting, I believe. Yes, I think I'll finish here.
Thank you, Professor. Any questions?
Yeah, Lindsay Patterson a few years ago did some interesting work on the use of circuits and paths, minimizing circuits and paths in design graphs.
Yes.
I mean, is this, you looked at that and see how it's connected with what you do?
Oh yes, it is connected, of course, and I knew that work, and it was more or less his idea for me. It is not exactly the same graph Patterson is looking at. His graph has only the treatments as points. But, for example, here, in this example, Patterson's graph would look like this. And the general idea in this, what is it called? What is the name for that network? He has a name for it. I call mine the design network. He calls it the variety concurrence graph. That's the word. The general idea is that whenever you have two treatments, you draw a connection between them for each block in which they meet. So it is not exactly the same graph, but you can show that for designs with equal block sizes, you can also give an interpretation as an electrical network to this variety concurrence graph, and the result is approximately the same, except for a constant factor. There should, I think the block size occurs as a constant factor somewhere.
Which work is that?
Sorry?
Whose paper was that?
Lindsay Patterson.
see, but CS Chang has done a lot of work connecting block designs with graphs.
Yes, pattern.
CS Chang from Berkeley.
Yes, he has also worked on it, yes.
Graph and block designs, well known in combinatorics many years. R.C. Bose started with the partial geometry, and from that, N.M. Singhi and many other people
Now, listen to the
contributed a great deal, and there is a vast literature in this area, and King and others also contributed.
Yes. But as far as I know, the electrical interpretation is not common. It exists, but
if the two graphs you are considering, one is the simple graph for the treatment, another is like your bipartite graphs, there are two sets, blocks and treatments.
yes. Yes, I suppose the term regular graph design comes from that interpretation.
And there are no further questions. Thank Professor Tjur for the interesting talk.